Guys, this is the last lesson here, like officially lesson. I'll do some others. We'll do lots of other things still in the book. Yes, this is our last book lesson here. So today we're looking at volumes of solids of revolution. Disks and washer methods are the two methods that we're doing today. And so what we have is, if we have a given base, you can create semicircular cross sections sticking up and out towards you. So they sort of, a little semicircle, a little bigger semicircle, a little bigger semicircle coming off the page at you. And we've created these little semicircular cross sections. Since the formula for the area of a circle is pi r squared, the formula for the volume of a circular cross section would simply be, there it is again, there's the area formula, your area. If we wanted to use circles, pi r squared times a little thickness, which of course then we could go ahead, we could pull the pi off because it's just a number, so we could pull that out in front and multiply it. And so what would happen here is we would have these, well, we'll just do this warm-up example. We're going to use this region bounded by y equals x squared. So here's y equals x squared, this top curve. And then y equals negative x squared. That's this downward-facing parabola. X equals 0 and x equals 1. Right here, that vertical line. So we have this lovely little region shown in the graph, and we want to create a volume using circular cross sections perpendicular to the x-axis. So what we want to have here is, imagine this is looking down on a circle, but we have this sort of circle shape that we want to use. So we want to make this a bunch of areas of circles, all stacked side by side. And so let's see, we know that the area, if we were doing this as we did on last Friday, we would, to find, well, I don't want to use A, I want to use the radius here. I need to find the radius. Well, I guess it's not really radius here. This would be a diameter of a circle, so I'm going to use D. Diameter equals. To find this diameter, we'd have to do top minus bottom. So top curve is x squared minus the bottom curve, so minus the negative x squared. Well, that gives me a diameter of 2x squared. But I actually don't want, I want the area of the circle. So how are we going to find the area of the circle? Cut it in half, yeah, because we really need the radius. That's what we really need. And so if I want, then I could do the area is pi diameter over 2 squared. Well, all right, so then that would be pi times 2x squared over 2, and then we square that. So there's our area, diameter divided by 2. That would give us the radius. Those 2's, of course, cancel out. Kind of nice. All right, so then there's our little area. There's our circle shape that we've figured out there. If I want the volume, then that would be integrating from 0 to 1 on the x-axis. The area is pi radius squared. Well, that's just pi x squared squared. And then times our thickness, dx. So there is our formula to find the volume if we use circles. All right, so we could do that. We could find all these little circles stacked together. I don't know if you can visualize what that looks like in your head. A bunch of little circles side by side, getting bigger and bigger in size. Yeah, it does. Yep, sure does. There's a little 3D image there. Sort of the shape. So we can also not only just think about it in terms of circles here, but we can create circular cross sections by revolving a very thin rectangle around the axis of revolution. These circular cross sections are more commonly called disks. So what we have today are volumes formed by revolving a region about a line. So we create what are called solids of revolution. And about the line we call the axis of revolution, which we'll be denoting with a little circular arrow. And so we have this formula for disks. We want a volume. And what we're doing is we're creating and taking, like this first example here, I have this region that is simply the curve y equals x squared. And what we want to do is find the volume of the solid formed by revolving the region bounded by y equals x squared, y equals 0, which is just here, this horizontal line, y equals 0, and the vertical line, x equals 1, about the x-axis. So we're going to revolve around the x-axis here. So this is our little notation that we use to show that we're revolving, we're spinning this shape around the axis. So what does that do? We have this little segment here, and what this is going to be is basically a radius. All right? And what we're going to do then is we're going to take this radius and we're going to spin it around that axis of revolution, and it creates the circle for us. It's a radius after all. All right? And so if we just multiply pi r squared, that'll give us the area of that circular shape. And if we add them all together between 0 and 1, that's going to give us a volume rotating circles around the x-axis. It creates this very cool shape. And so the volume, well, let's see, we have our area is pi r squared, but that radius, what is that radius? How do we get that height of that radius? Yeah, it's just landing on our curve here, which is defined by y equals x squared. Well, there it is, just x squared. And then we have to square that. So we get our volume equal to the integral, again, from 0 to 1 of pi x squared, quantity squared, dx. And if I want, I can take the pi out in front just to make life a little bit easier. And of course, you could multiply x squared. Squared could be x to the 4th. But you'll notice it's the same thing. As above, we do get the exact same thing. We just don't have a bounded region where we have to do the top minus bottom scenario. Okay? So it's the same idea. It's just that we're sort of consolidating it into saying, hey, we can create circles if we just have a radius. Okay? All right, let's look at number 2 here. Find the volume of the solid formed by revolving the region in quadrant 1, bounded by y equals x squared, x equals 0, and y equals 4. All right, well, that's kind of interesting. Here's our line y equals 4. X equals 0 is this vertical line. And then we have y equals x squared, which of course we know goes from 0, 0, 1, 1, and 2, 4. So there's half of it. And they only want it the region in quadrant 1. So that's all I'm going to draw here. So then the question is, we want to find the volume by revolving the region in quadrant 1 about the y-axis. So we're going to revolve around the y-axis here. So we're spinning this quadrant, this shape here in quadrant 1. We're going to take that shape and we're going to spin it all the way around that vertical axis. What does it create? What is that shape to you? If you were to spin it around the y-axis. Kind of like a bowl. Yeah, I would call it a bowl. A cone maybe would have more straight sides. But yeah, so a little bit of a bowl shape. if you were to spin this around the axis. That's sort of an important thing to be able to visualize. And so my question to you is if we spin it around the y-axis, are our slices going vertically or are they going horizontally? Yeah. So what we have here is we have this horizontal, distance. Well, if we're going horizontally here, I need to get to this curve edge. Do I need it to be in terms of y or in terms of x? It's already in terms of x. Well, it needs to be in terms of y. Yeah, we're going horizontal slivers here. So we're going to rearrange this formula. This is x equals the square root of y. It is just the positive side of that radical curve. We don't need the negative side. All right, so there we are horizontally. Now we're going to go in terms of y. And again, we're going to take this, basically this radius, which happens just to be the square root of y, and we're going to take it and we're going to spin it around that y-axis, creating our discs. And of course, there's lots of those discs. We could spin one down here that's much smaller. And you can see we get this sort of bowl sort of shape as we go. It's very cool. All right, so once again, our radius, the area of the disk is pi r squared, and our radius is what? Square root of y. That's all it is. We're going from the axis to our curve, which we've defined as radical y. All right, so there is our little shape for the area. Now if we take all of these disks and we integrate them, what is our upper and lower bounds here on our integral? So we're going from the bottom all the way to the top of our shape, okay? Yeah, so not from -2 to 2, that would be in terms of x. So we want everything in terms of y. So we're going to use the y. So from 0 right here all the way up to 4. All right, so that's very good. Everything needs to be in terms of y in this case. All right, so we have area. I'm going to put the pi out in front. And then, of course, the square root of y squared is just y. All right. And we actually do want to find this volume, not just set it up. So we can go ahead and integrate here. We got a pi out in front. And what is integrating y? Over? Yeah. Y squared over 2. And integrating from 0 to 4. So we have 4 squared is 16, over 2 is 8, so it's 8 pi. And then plugging in a 0, we'd have 0 pi, which is just 0. So we get 8 pi for the volume. Okay, how are you feeling about discs? All right, just circles. You just have to figure out, are we in terms of x or should everything be in terms of y? Really is the key there. All right, so now we're talking about washers. So when we have a region revolved about a line that is not one of its boundaries, which is what we were doing before, we were immediately adjacent to our boundaries, okay? A volume is formed by volumes, sums of washers, disks that have holes in them, really, if you will. And so just like we did before, there's a couple of ways we could figure it out. We could do the volume from A to B of pi r squared dx or dy. So we could take the area of the outer section, the big radius, if you will, and we could subtract the integral from A to B of pi little radius squared dx or dy. So we could do this a couple of different ways. We could take the big volume and subtract away the little inside volume. Okay, that would give us an appropriate volume, if we will. Or you'll notice if we did that, the volume of the outside minus the volume of the inner region. Well, they have a bunch of stuff in common here that we can sort of factor out, which is what's going on here. We're factoring out the pi from both of those expressions, and we're really sort of factoring out the integral of both of those and leaving just big R squared minus little r squared, where big R represents the outer radius and little r represents the inner radius. However you set these up, whether you do it this way or this way on the AP test, or, I mean, you could even do the volume is the integral from a to b of pi big R squared minus pi little r squared dx. Like, you could do it this way as well. Again, the pi's just factor out in front. It all works. I left off the pi multiple times. Okay, so just be aware. The pi is really important. All right. Again, pi r squared is just the area of a circle, and so we have to consider that big radius. So let's try a few here. We want to set up integrals for the volumes of solids formed by revolving the region bounded by y equals negative x squared plus x. So that's this downward facing parabola, and y equals 0. And for problem A, we're going to revolve about the x-axis. So we're revolving right around our x-axis here. We need to figure out our limits here, our upper and lower bounds on our integral here. I need to know where it's crossing the axis, so where our curve is equal to 0. So here's our curve. Negative x squared plus x is equal to 0. How do we solve that? Double bubble, take out an x. Yeah, it has a greatest common factor here. We can undistribute the x. We get a negative x plus 1. And so we get x is equal to 0, and here x is equal to 1. So we see that on our curve, 0 to 1. So that is in the x-axis, and what we're doing then is we just have this simple radius here going from our x-axis up to our curve, and of course that curve is just y equals negative x squared plus x. So if we want the volume, and we're right adjacent, like we're right around our, there's no gap in these circles, okay? You'll see in the next one. We're integrating from 0 to 1. And pi radius squared, and our radius is defined by our little equation here, negative x squared plus x dx. Okay, so that is just discs. That's just creating the little circles right around our curve here. Lots of little circles. I guess it'd kind of look like an eyeball when you're done. A football. This is the football shape, yeah? You see that when it's done? It'll be a little shape of a football. Yeah? Okay. All right, so here we have another one. We are revolving about the line y equals negative 1. So you see the little arrow they've drawn in here. And you'll notice here, we have the same shape. It's going from 0 to 1 on the x-axis. But now, this is going to spin like all the way around, come back to the top. But then there's this inner radius that's going to spin around as well. And so we get this weird donut kind of shape to it, okay? It's very square through the middle of it. Not square, it's round, perfectly cylindrical through the middle of it. And the outer edge is rounded off, okay? Crazy shape here. This is a washer, which you can clearly see. We got a washer shape. So the volume, integrating from 0 to 1, we have a pi. I'm just going to move the pi out in front. And what I need is big radius squared minus small radius squared. What is our giant radius? From -1 all the way to the top of the curve. How do we figure out that big R? It's the same thing we did on Friday. Top minus bottom. Okay, so the top here is negative x squared plus x minus the -1. Okay, top minus bottom. The little r, again, here's the little r, drawn it in here. What's the formula for that? Yeah, the top is 0. It's y equals 0, if you will, minus the -1. It does just have a radius of 1, which of course does clean up to 1. And so to get our big R minus little r, we have negative x squared plus x minus the -1 turns to plus 1. And then we are going to subtract 0 minus the -1, which is just 1. Which of course, plus 1 minus 1 would clean up. Oh, what did I miss here? What did I not do? I didn't square my radii. All right. Woof. So we're squaring our big R and we're squaring little r. Don't forget, which I tend to do. Always a good idea maybe just to write down pi equals the integral of big R squared minus little r squared dx. Okay. Which I should definitely do. Okay, another one. Here we are revolving around the line y equals 2. So again, this is above. And so we have this same shape that crosses the x-axis rather at 0 and 1. And again, we are going to take this figure and it's going to spin around this y equals 2 line. So there's the outside radius. And then again, here's the inside that gets spun around, and my picture is not beautiful there. But once again, we need to find those radii. So the big radius goes from our axis of revolution to here. There's big R. How do we figure out big R? Top minus bottom. So big R is going to be, this is the line y equals 0. Yeah, just 2 minus 0, which is just 2. And then we have little r, which goes from my axis of revolution to my curve. So there's little r. What is little r? Yeah, 2 minus. Yeah, so 2 minus the entire negative x squared plus x. I wrote my thing a little bit too smushy there, but that's 2 minus the quantity, negative x squared plus x. So again, anytime you have a subtraction, follow with parentheses just to make sure we distribute that right. So that'd clean up as 2 plus x squared minus x, if you will. Okay, so our volume is going to be pi integrated with r squared minus little r squared dx. I'm going to write it down so I don't mess it up this time. All right, pi out in front. We are again integrating between 0 and 1. And we have big R squared, which is just 2 being squared, minus little r squared, which is minus the entire 2 plus x squared minus x quantity squared, and don't forget your dx. All right, how does that feel to you? Does that feel okay? Feels okay? All right. Kind of an interesting process. All right, example 4, set up integrals for the volumes of solids formed by revolving the regions. Bounded by y equals x squared. So that's this curve, y equals x squared. And the line, y equals x plus 2. Here we're taking vertical slivers. And on this particular one, we are rotating about the x-axis. So we are spinning around this x-axis. So I always have to draw what I'm looking at here. So I'm going to get this top edge that's spinning around and the bottom edge. So once again, I'm seeing a washer kind of shape. But I need some information here because we're going to spin around this entire region, the shaded region. I need to figure out these points of intersection. How do we do that? Yeah, where do they equal each other? They're both in equal to y, so we can just set them. We want to know where the parabola equals the line x plus 2. I'm going to go ahead and push everything over to one side. We get x squared minus x minus 2 equals 0. And then what do you do from there? Double bubble. I love that you guys have adopted double bubble. Don't say silly things like factor. That's crazy. All right. What times what gives me a negative 2? Negative 2 and a positive 1. Very good. And so we get solutions for x at positive 2 and x equals negative 1, which we do sort of see there. So there is our between those two intersection points. So those are my limits on my curve. And let's see, I guess I need my big R and my little r. My big R goes from my axis of rotation to the farthest point. That's my big R. What's big R? Just x plus 2. Yep. Just that top curve. Good. And little r is right here from my axis of rotation to the bottom curve. So again, top minus bottom. Oh, interesting. So this is my radius actually right there. Yeah. So if I take that pink radius and I subtract away the orange, what I'm left with is the black. Yeah. Is another way to think about that. Yeah. So my little radius goes from, it's just from the axis to the bottom curve. Bottom curve to axis. X squared minus 0, yeah, or just x squared. This is also x plus 2 minus 0, if you will, top minus bottom. All right, so then for my volume, it's going to be pi integrating from negative 1 to 2, big R squared minus little r squared dx. And since I wrote it down, now I'm not going to forget anything. Pi equals pi integrated from negative 1 to 2. My big R squared is going to be x plus 2 quantity squared. And then minus little r squared would just be x squared quantity squared. And this is where I think that, you know, it takes a second to write this out, but you're less likely to forget the squared part, which I did already today. So again, r is x squared, and then we have to square that, so we get x to the fourth. But this happens a lot on the AP test, where this is all they want. They just want you to set it up. So it's important you're very, very clear. Don't simplify because you don't need to. We don't want to make any extra mistakes. All right, now on this one, we want to integrate about the line y equals 4. So here's the line y equals 4, and we're going to spin around this line. All right, and so now, imagine here, if I'm spinning around this line, I have this inside piece that's going to spin around. So there's one, thank you, sorry, there you go. So this inside section spins around that y equals 4 line, but then we have this outer section that's also spinning around, coming back. All right, so again, it's a washer method. And so we have this inside radius, so I'm going to call that little r here. And then this big radius, there's big R. All right, we are still integrating vertically, so we're still going from -1 to 2. All right, so what is our big radius? Four minus x squared, yeah, top minus bottom, so that the top is 4, minus our bottom here, which is y equals x squared, so just x squared. Okay. And then the little radius, just here, that little blue line, I should have done an orange. What's that radius? Yes, 4 minus, careful now, 4 minus the quantity, x plus 2. And that is where big mistakes happen, right? Because we have to subtract the entire curve, all right? Okay, so again, I'm just going to leave it like that, free of mistakes. We have pi integrating from -1 to 2, a big R squared minus little r squared dx. And so, -1 to 2, big R squared is 4 minus x squared, and then it is squared, minus little r. So little r is 4 minus the quantity x plus 2. Again, that would clean up, and then we have to square that. Lots you could do there to clean that up. If they did ask you to integrate, I would absolutely distribute my negative here, 4 minus x minus 2, clean it up. We'd get 2 minus x. We would have to FOIL this out, FOIL that out, combine like terms. I would absolutely do it that way, but that is definitely one you could see on the AP test, having actually find the volume of. Okay, do you have questions for me? All right, great. You have adults math, enjoy.